The discovery made by NASA's Space Telescope at Comet 3 I/Atlas has sparked an unexpected wave of excitement among astronomers, as it represents a breakthrough in the study of how comets evolve, especially those originating outside our solar system. What makes this discovery even more significant is not only the nature of the find, but also the comet's extraordinary location at the time the data was captured. Comet 3 I/Atlas is no ordinary celestial visitor. It is an interstellar object, one of only 3 such comets humanity has ever observed, placing it in a category so rare that each new piece of information about it reshapes what we know about the birth of planetary systems. Since its discovery on July 1, 2025, astronomers have been eager to examine every detail of its structure, composition, and behavior. Unlike common comets bound to the Sun by gravity, 3 I/Atlas follows no orbital path around our star. Instead, it is merely passing through the solar system on a long journey that began in a distant region of the Milky Way. Once it completes its swing past our Sun, it will continue its voyage back into deep interstellar space and will never return, making this a once-in-a-civilization opportunity to study a relic of another star system. The comet is believed to be around 7 billion years old, placing its origins long before Earth itself formed. That extraordinary age makes it the oldest comet ever detected, and effectively a frozen time capsule from the early era of planetary formation in its original star system. Because of this, scientists see 3 I/Atlas as a pristine sample of primordial material, its chemical structure likely unchanged since before our own solar system existed. As the comet approaches the Sun, its surface warms and begins to release gases trapped inside for billions of years. This process provides researchers with rare access to ancient, unaltered matter that predates everything humans have ever known. Recognizing the tremendous scientific value of this moment, space agencies around the world mobilize their instruments to observe the comet from every possible vantage point. Even Mars rovers and orbiters were directed to take measurements, while the comet remained hidden from Earth due to its close proximity to the Sun, demonstrating the global urgency behind understanding this interstellar traveler. A major contribution came from a team at Auburn University in Alabama, who successfully pointed NASA's Neil Gehrels Swift Observatory toward the comet during a period when ground-based telescopes struggled to capture useful data. Swift, which operates in ultraviolet wavelengths, detected a faint but unmistakable signal of hydroxyl gas, scientifically known as OH, surrounding the comet. This chemical signature forms when sunlight breaks apart water molecules, meaning it is a direct indicator of the presence of water ice on or within the comet. Detecting hydroxyl is often the key method astronomers use to determine the activity level of a comet, because as the Sun heats the comet's nucleus, water vapor escapes and breaks down, producing this ultraviolet glow. The ability of Swift to observe wavelengths of light that never reached the Earth's surface allowed it to see what no ground instrument could, revealing that 3 I/Atlas behaves much like comets native to our own solar system. This discovery represents a turning point in the study of interstellar objects. Previously, astronomers could only speculate about how comets formed around other stars, and whether they shared chemical similarities with those formed near the Sun. The presence of hydroxyl gas around 3 I/Atlas now provides compelling evidence that at least some interstellar comets contain water in a similar form and undergo the same type of activity when exposed to solar radiation. This opens the door for scientists to apply their existing knowledge of cometary evolution to a foreign object, allowing for direct comparisons rather than educated guesses. By analyzing how much water the comet releases, how quickly it becomes active, and how its tail develops, researchers can start mapping its behavior onto the patterns seen in typical solar system comets, gaining insights into the basic chemistry and physical processes that shaped it billions of years ago. Studying an interstellar comet's water content also has broader implications for the universal question of how planets form and whether life-supporting environments are common across the galaxy. Water is a fundamental ingredient for life as we understand it, and its presence in a comet originating from another star system suggests that the building blocks of life may be widespread rather than unique to our solar system. If interstellar comets routinely carry water, it implies that planet formation in other regions of the galaxy may follow similar chemical pathways, increasing the likelihood that habitable worlds exist elsewhere. The detection of hydroxyl gas is not merely a piece of chemical trivia. It is a clue to the broader processes that shape planets, atmospheres, and potentially even life itself. Furthermore, the discovery underscores how technological advancements in space-based observatories are transforming modern astronomy. Ground telescopes are limited by Earth's atmospheric filtering, which blocks certain wavelengths of light. In the case of 3I/Atlas, the essential ultraviolet signatures from water breakdown were invisible from the surface, creating a blind spot in traditional observations. Swift's ability to see beyond the atmosphere allowed astronomers to overcome this barrier and produce a result that would have been impossible from Earth. This achievement highlights the increasingly crucial role of space telescopes in studying phenomena that lie outside conventional observational limits. As more advanced space observatories are developed, including next-generation ultraviolet and infrared missions, scientists will be better equipped to capture detailed data from other rare interstellar visitors in the future. The study of 3I/Atlas also contributes to a growing field of research focused on interstellar objects, a topic that has exploded in interest since the detection of the first known interstellar object, Oumuamua, in 2017, and the interstellar comet 2I/Borisov in 2019. Each of these objects offered glimpses into the diversity of material drifting through the galaxy, but none stayed long enough or passed close enough to provide the kind of clarity Swift captured from 3I/Atlas. Oumuamua's lack of a visible tail and its unusual acceleration puzzled scientists, while 2I/Borisov behaved more like a typical comet, but was observed only briefly. With 3I/Atlas, astronomers finally have a chance to study an interstellar comet with the full toolkit normally reserved for solar system comets, making it one of the most valuable subjects in cometary science. Additionally, the comet's extreme age suggests that it formed during the early stages of its home star system's development, perhaps when the system itself was still a swirling disk of dust and gas. Whatever conditions shaped it, the comet has remained almost completely unchanged for billions of years due to the isolation and cold of deep space. Its chemical composition, including the water detected now, likely matches the original ingredients present in its natal disk. This makes 3I/Atlas an extraordinary sample of ancient cosmic material that predates Earth by a vast margin. Studying it may help scientists determine whether the processes that created planets around our sun, such as the collapse of dust clouds, the merging of icy bodies, and the chemical reactions leading to organic compounds, were unique or universally common. The fact that Mars orbiters and rovers were redirected to assist in observing the comet also emphasizes how seriously scientists view this opportunity, since the comet entered a position that made it temporarily invisible from Earth. Having instruments on Mars offered an alternative perspective not blocked by our planet's position relative to the Sun. This rare multi-planet observational strategy demonstrates the new era of interplanetary cooperation in scientific research, where multiple worlds serve as platforms to collect data on shared celestial events. As humanity expands its presence in the solar system, future comets may even be studied from lunar bases, Martian laboratories, or deep space telescopes stationed far from Earth. Overall, the discovery of hydroxyl gas at Comet 3I/Atlas marks a milestone in our understanding of interstellar objects. It shows that at least some comets formed around other stars contain water and behave similarly to those in our solar system, pointing toward universal patterns in comet evolution. This breakthrough deepens our understanding of how comets evolve, how planetary systems form, and how widespread life-supporting elements may be across the galaxy. With every new observation, astronomers come one step closer to understanding not only the history of distant star systems, but also the larger story of the Milky Way itself. As 3I/Atlas continues its journey out of the solar system and into the dark reaches of interstellar space, It leaves behind a trail of knowledge that humanity will continue to study for decades to come.